throw up on that stuff. Okay, so we talk about these measures of center and spread. Let's talk about what they mean. We're talking about something called the empirical rule. And each textbook does it a little bit differently. Some textbooks go by what's called an exact empirical rule, and some go by what's called an approximate empirical rule. And I think they changed in your newest version here. So for what it's talking about is it's talking about this bell curve. And pretend that looks like a bell. The center of that bell curve is the mean. Or the median or the mode. If it's a good distribution, they're all the same, right? And if we go out away from that in steps, and that step being 1 standard deviation. So this would be subtracting 1 standard deviation. Between the mean and 1 standard deviation below is about 34% of the data. The same goes in the other direction. If I go 1 standard deviation above, plus 1 standard deviation. About 34% is between the mean and 1 standard deviation above. If I go 2 standard deviations below, if I subtract another standard deviation, so we're 2 below here. Between 1 and 2 standard deviations below is about 13.5% of the data. Same on the other side. Between 1 and 2 standard deviations above is about 13.5% of the data. Between 2 and 3 standard deviations below is going to be about 2.35%. And the same on the other end. Outside of 3 standard deviations on each end is going to be 0.15%. So that's literally 15 out of 10,000 will be more than 3 standard deviations above the mean. 15 out of 10,000 will be more than 3 standard deviations below the mean. But right now this is probably meaningless to you. Let's throw in some numbers here. Let's say that for this class, the mean score is 80%. The standard deviation of 6. These percents will never change. Those percents are always the same. What's going to change is the numbers that go in down below here based on the mean and standard deviation. So the mean is 80. So the center number here is 80. What would this number be? Well, we're subtracting 1 standard deviation from the mean. The mean is 80. The standard deviation is 6. So we subtract to get 74. Then we subtract the standard deviation of 6 again to get, oops, not 70 anymore, but 68. We subtract it again to get 62. Going the other way, if we add the standard deviation, what number would this be? 86 and 92 and 98. So what this is saying is, throughout the history of this class, about 0.15% of students got better than a 98% in the class. About 34% get between an 80 and an 86. What percent do better than 86? Well, here's 86, right? Better than that would be above that. If I add those all up, I'm going to get 16%. Only 16% do better than an 86 for this class. Does that all make sense? These are always given. Those are always under the curve. The only thing that changes are these numbers down here, and those are based on your mean and standard deviation. I'll make that curve a little better. I do look lopsided, but not quite that lopsided. That one's a little better. Okay, so how would you use this? Let's say you are offered a job. And they offer you a salary or a wage of $16.20 per hour. And you want to know if that's good or bad. So you look at all the jobs in the area and what the starting wage has been. Let's say in that area, starting wage at different jobs has a mean of $15.10 per hour and a standard deviation of $1.10 per hour. What number is going to go in the middle here? $15.10. The mean always goes in the middle. What's going to go right here? The mean minus the standard deviation. So $15.10 minus $1.10 is $14. What'll go here? $12.90. And this one will be $11.80. Good. Going this way, what's going to go here? $16.20. And here? $17.30. And here? $18.40. What percents go in here? Trick question. Always the same. Those are percents, yes. There. That better? Don't get used to it. Okay. So there they are. So your offer of $16.20 falls right here. That means you're getting a better starting salary. If you add all these up, that adds up to 84%. You are getting a better starting wage than 84% of the people in that area. Does that make sense? Maybe tempted to take that one? Yeah. Yeah, be right in the middle. So another example. So let's say you take that job offer and you're going to have to move. You decide you want a 3-bedroom, 2-bath house. That's actually the most popular house size right now. 3-bedroom, 2-bath. The most valuable per square foot is 3-bedroom, 2-bath. You do your research, and in that area, the mean selling price. Now, I'm not talking listed price or asking price. I'm talking selling price, what they actually sold for, of 3-bedroom, 2-bathroom houses in that area is $124,000. The standard deviation of $18,000. So what's the center number going to be here? 124. I'm going to leave the zeros off. What's going to go here? 124 minus 18 will be 106. Good. And then next, minus another 18. 88. And then minus another 18. 70. Going this way, plus 18,000. 124 plus 18,000 is 142. plus another 18, 160. Right? And then another one. There you go, 178. And of course, these percents are the same. You can use your notes, so just write them down. Make sure you have them somewhere you can find them. Let's say you find a home that you just absolutely love. It's exactly what you want. It's listed at $160,000. Your realtor says, yep, you're never going to find anything like this. You got to put in an offer right now. No, give them their asking price because they're not going to budge. Well, what does this curve tell us about that? 160,000 is right here, isn't it? It tells us that if we look at this, what percent of homes with 3 bedrooms and 2 baths in that area cost more than 160,000? If I add those up, I get 2.5%. Only 2.5% of houses cost more than 160,000. Chances are one of two things are going to happen. Either they'd be willing to take a lower price because they're asking too much, or you can find a house that's cheaper that you still like. Because 97.5% are going to be cheaper. You decide that you are going to set your limit. You're going to buy, your range is going to be 88,000 to 142,000. You'll go down to 88,000, you don't mind doing a little work, but you can't afford to go over 142,000. What percent of houses are going to be in that range? Well, here's 88. Here's 142. So add up those percents in between there. What do they add up to? %81.5%. So by giving yourself that range, you are including 81.5% of all the houses in that size are ones you're going to be willing to look at. Now, the one thing you'll notice here, one of the weaknesses of this is if our number doesn't fall right on one of these standard deviation steps, this curve doesn't tell us much. If that house was priced at $150,000, I mean, still technically use the curve. $150,000 is somewhere in here. So we know it's somewhere in between these percentages. I mean, if I add these all together, that's 84%. So we know that it's more expensive than at least 84% and a little bit more. If we add these up, it's 2.5 plus part of that 13.5. We don't know how much though. So we know that if we added the 13.5, that's 16. There's less than 16% of the houses are more expensive, but we can't get an exact number. So for this to be really exact and be useful, the number we're looking at has to fall on one of those steps that's created by the standard deviations. But we can use the standard deviation and mean for something called the z-score. And the z-score does, it allows us to compare two things that are from different populations. Let's stick with this buying a house. But let's say you have 2 job offers in different neighborhoods, different areas. And the housing prices are very, very different from one area to another. So you want to look, you've analyzed the salaries and the jobs, and you like both jobs equally. You want to decide which one you're going to be able to find a better place to live. And by jobs are equal, I'm saying that the wages reflect cost of living. So even corrected for cost of living, the pay is exactly the same. So let's say in area A, you find a house that is $132,000. In the area of job B, you find a house that's $118,000. Now, like I said, even area A has more expensive housing, more expensive cost of living. But the wages compensate for it. So you're going to get paid more if you go to job A than you would job B, but it works out to be the same because cost of living is more in that area too. Let's say over here that the mean, you're still looking at that 3-bedroom, 2-bath house. The mean cost of a 3-bedroom, 2-bath house in area A is $140,000. So standard deviation of $16,000. In area B, the mean cost of a house is $128,000. Oops, let's not do that. Let's do $124,000 for the standard deviation of $10,000. Which house is more expensive according to its area? Well, the Z-score takes a number, and from that we adjust that number for its population by subtracting the mean of the population from that number, then dividing that difference by the standard deviation. So for area A here, that house, the Z-score, we had a $132,000 house, minus a mean of $140,000. Divided by a standard deviation of 16,000. So 132 minus 140 is a negative 8,000. Minus 16,000 is a negative 0.5. What that is saying, the negative means that that price is below the mean. It's less than the mean. The 0.5 is saying it's half of a standard deviation below the mean. Let's look at this one, the Z-score. So the house is 118,000 minus the mean of 124,000 divided by the standard deviation of 10,000. 118 minus 124 is negative 6,000 divided by 10,000 is a negative 0.6. Again, the negative means it's below the mean, but it's 0.6 of a standard deviation below the mean. So compared to its own area, this house is cheaper because it's more standard deviations below the mean in that area. Does that make sense? Let's look at another way. Let's say you take your entrance test to get into school. Take a math test, you take an English test. On the math test, you score a 34. On the English test, you score a 38. You think, well, you did way better in English than you did in math. But let's say the mean in math is 28 with a standard deviation of 4. The mean in English is 33. The standard deviation of 3. Calculate the Z-score for the math and for the English for me quick. Okay, for math, our Z-score. 34 minus the mean of 28 divided by the standard deviation of 6. 34 minus 28 is 6. Standard deviation is 4, not 6. I think I said 6. So 34 minus 28 is 6. We're going to divide by the standard deviation of 4, which is 1.5. That's positive, which means it's above the mean. Your math score was 1.5 standard deviations above the mean. That's pretty good. If you think back to that bell curve and those percents, that's somewhere between the 1 and 2 standard deviations above the mean. So you're better than more than 84% of the group. For English, your Z-score. Your score was 38 minus the mean of 33 divided by a standard deviation of 3. So 38 minus 33 is 5. 5 divided by 3 is 1.67. Your English score is 1.67 standard deviations above the mean. 1.7 would be okay. So the English score is more impressive because it's more standard deviations above the mean. Does that make sense? Let's say you are managing a store and you're going to fire one salesperson. And you've got it down to 2 people. We'll call them Pat and Lauren. And you decided that next week, whoever has the worst week is the one who's going to be gone. So let's say Pat sells $1,200. And Lauren sells $2,800. Who's gone? Pat? Well, we don't know yet. Let's say Pat works in toys. And the mean for that week for all people in toys was $2,000. With a standard deviation of $300. That would give Pat a z-score of, what number goes first? 2,000? 1,200. The actual number. Then we minus the mean divided by the standard deviation. So 1,200 minus 2,000 is a negative 800. Divided by 300 is a negative 2.67. So Pat was 2.67 standard deviations below the mean. Let's look at Lauren. Lauren works in electronics. The mean for all people that worked in electronics that week was $4,000. Standard deviation was $500. So the z-score for Lauren was 2,800 minus the mean of 4,000 divided by a standard deviation of 500. 2,800 minus 4,000 is a negative 1,200. Divided by 500 is a negative 2.4. So Lauren was only 2.4 standard deviations below the mean. So the worst score is Pat. Pat did a worse job of sales, so Pat is gone. Any questions? The 1,228 won't always work out that the 1,200 is lower. Because let's say that this was a standard deviation of 400 instead of 500. Well, now we look at that, and okay, 2,800 minus 4,000 is still going to be 1,200. But negative 1,200 divided by 400 would be a negative 3. So there, Lauren would have been worse. What it's doing is it's taking the data and it's comparing it. You can't compare the numbers to each other. You have to compare them to how they stand within their own populations. And then you can compare that relationship to their own population to each other. Okay, I think you guys have suffered enough. There is a new quiz. Yeah, the 21st. There'll be one more. There'll be one on Friday yet. So the new quiz is due Wednesday, of course, at 11:59 p.m. There is a new homework that is due on Thursday. Thursday we will talk about percentiles and quartiles and maybe some box plots. And then we will do a lot of review for the final test. So Thursday's a big one. If you see people that aren't here, tell them they may want to come on Thursday. I have a nasty habit of not recording the review for the final test if a lot of people aren't here. Just kind of my little, yeah. I'm saying that on recording, so those of you at home that aren't here can hear that. You may want to be here.